So for the first part of this question, I've just asked you to expand the square of this term. There's three terms in there, so we've got to think a little bit. I guess this is kind of slightly advanced multiplying out brackets stuff. Maybe we'd expect, maybe we'd expect to get 9 terms by doing something like 1x x squared times 1x x squared and multiplying everything out. Different ways of doing this. I think however you do it, you get an x squared, you get an x to the 4. Those are the squares of each terms, and then you also get 2 lots of the product of pairs of terms. So importantly, you get an x squared term from squaring the x, that's here, and you also get an x squared term from times when you multiply 1 by x squared. And there are 2 of those because you might take the 1 from the first bracket and the x squared from the second bracket, or the x squared from the first bracket and the 1 from the second bracket. Next part of the question wants us to think about what the coefficient of x squared would be if we expanded this. Now I don't want you to go and expand that because it's got something like 27 terms if you expand it the slow way. Instead, I'd like it if we could think about where you get those x squared terms from. So there's sort of 2 ways to get an x squared, aren't there? You could have a 1, an x and an x. So 1 from the first bracket, maybe, an x from the second bracket and an x from another bracket. Or permutations of that. Maybe we take x then 1 then x as we multiply out these brackets. Here I'm thinking about multiplying out these brackets. The different terms you get are from different combinations of, as I multiply out, I'll get something from the first bracket multiplied by something from the second bracket multiplied by something from the third bracket in each case as I do the multiplication out. So I need to think about ways to make x squared. So I could do it like this, or I could make it like this, or permutations of that choice, where I'm taking the 1 from one of the brackets, a 1 from another bracket, and an x squared from another bracket. Now there are, so I've mentioned permutations or different orders to do these terms in, because those are each going to give me an x squared. Now let's think really carefully. There are 3 ways to do something like this. 3 ways to do something like this first line, because I could take the 1 from the first bracket, I could take the 1 from the second bracket, or I could take the 1 from the third bracket. And there's also 3 ways I could do it like this, because I could take the x squared from the first bracket, the middle bracket, or the third bracket there. So that's 6 different ways of doing 6 different ways of getting an x squared term out there. Cool, right, okay, so I get 6 for that part. Okay, for the rest of this question, we're going to let n be a positive integer. Okay, so now we're going to think about what happens in the kind of general case as we go up to 1 plus x squared to the power of n, and then I've got some extra bits as we slowly move towards doing that math question. But this idea of different combinations of how we select terms from those brackets is how I'm going to do the next part of this question as well. Okay, so this part asks, what happens when we do 1 plus x squared all to the power of n? Now, I suppose x squared is quite small, and most of the terms that you get when you do 1 plus x squared to the n, you get things that are quite large powers of x, right? All the way up to x to the 2n. Here, I suppose our choices are we want to take either use lots of 1s and just 1 x squared. That's one way to make x squared, or lots of 1s, 2 x's. So as I multiply out these brackets, I could have choosing just one to have giving an x squared. So I look through all of these brackets and I'll get an x squared whenever I choose 1 from most of the brackets, but x squared from just one of them. And I'll get also get an x squared if I choose x from the middle term in the bracket there from exactly 2 of the brackets as I multiply out these n brackets. Okay, and I think a little bit in terms of binomial coefficients now, in terms of choosing terms. So how many ways are there to do this first thing? So I'm using lots of 1s and just 1 x squared. I've got to choose one of the brackets to pick my x squared from. And there's n brackets, because I'm doing this to the power of n. So there are n, this happens n times. Okay, one for each bracket. So maybe I take the x squared from the first bracket and then loads of ones. Maybe I take the x squared from the second bracket and 1 from all the other ones. Or maybe I take the x squared from the last bracket and 1 from all the others. There are n ways to do that, and each is going to give me an x squared. The other thing is if I pick x from exactly 2 of the brackets and lots of ones. Okay, so there are, using binomial coefficients, I've got to choose 2 of my brackets. The notation for this NC2 or N2 stacked up like that. I think that's equal to something like n plus 1 over 2 or something, but this notation is fine, or this, any of these is okay notation. So my final answer, I suppose, is either of these are going to give me an x squared. So my final answer is going to be, total is n plus n choose 2. And if I really think about it, then what this was really n choose 1. Now n choose 1 is equal to n, but I'm choosing, for kind of neatness, n choose 1 plus n choose 2. So I'm choosing 1 out of there. Okay, so here I think I've got, let's imagine this, I've got 1 plus x plus y to the power of n, so that's like 1 plus x plus y, 1 plus x plus y. I've got n brackets, and I want x cubed y to the 5. The only way I'm going to get that is if I choose 3 x's and 5 y's from these brackets. So I suppose I need to choose 3 of my brackets to give me an x, and then I need to choose from the remaining brackets 5 of them to give me a y. This is going to be, I think, n choose 3 for the number of ways to pick 3 brackets to give me x's. I'm going to choose 3 brackets to give me x's, and then whatever choice I make, I've got n minus 3 left over, and I need to pick 5 of those to give me a y. So I think it's this, which I've done quite quickly, to say I need to choose 3. So first choose 3 brackets. First choose 3 brackets to give x. And then in each of those cases, then choose 5 brackets from remaining ones to give a y. Okay, a little bit of algebra. I saw someone in chat give me a different solution here, so I'm going to try and rearrange this bit. N choose 3 is n factorial over 3 factorial n minus 3 factorial. And n minus 3 choose 5 is n minus 3 factorial over 5 factorial n minus 8 factorial, which cancels down a little bit to give me something like n factorial over 3 factorial 5 factorial n minus 8 factorial. I saw someone in chat, Ben says something like, they're going to rearrange that. Yeah, so that's equal to, someone in chat says n choose 5 times n minus 5 choose 3, which is the same thing. I've gone off the bottom a little bit. So n factorial over, this is n factorial over 3 factorial 5 factorial n minus 8 factorial. And just, I saw Ben in chat write something like n choose 8. This is related to n choose 8 somehow, multiplied by something, because it's not quite n choose 8, because this is not quite 8 factorial. It's this times 8 factorial over 3 factorial 5 factorial. The reason it's not just n choose 8 is because we're choosing 8 special brackets, 8 brackets to not be 1, but then we've got a choice inside there of which ones to use to take an x from the bracket and which ones to take a y from the bracket. I suppose that's a different way of thinking about it. It's n choose 8 divided by, hey, I know what that is, n choose 8 times 8 choose 3. And actually all of these turn out to be the same number or the same expression in terms of n. There's different approaches. Is there a shortcut to this? Well, there's different ways of thinking about it. I quite like this way actually. Choose 8, so the logic here is like choose 8 brackets to not be 1, to not give 1. Then out of those 8, then pick 3 to give an x out of those 8. So choose which 8 brackets are going to be special brackets, and then decide, well, some of these are giving me x and some of them are giving me y. Oh, hang on a minute, I want x cubed y to the 5, so I better pick 3 of them. Okay, last part of the question is a math question. It was multiple choice. I haven't given you the options. We're just going to have a go at it. We're looking for the coefficient of x cubed y to the 5, same thing as before, but now the terms inside here are a bit different. So when I multiply this thing out, 1 plus xy plus y squared, I'll have n of these brackets like this. And you know, each term I get when I multiply these out will be something like, you know, I could take, I'm doing a kind of first outside, inside, last kind of thing on these brackets. I'll get loads of different terms from, say, this multiplied by this, multiplied by blah, 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 multiplied by this. And I'll get lots of other terms like that as well, taking combinations of each term, each combination of terms from those brackets. Okay. Right, so I want to think about how we make, x cubed y to the 5. So I want x cubed y to the 5. In general, when you multiply out terms from these brackets, you'll get all sorts of nonsense, up to like loads. If you take y squared from each bracket, you're not going to get x cubed y to the 5. You're going to get y to the 2n or something, which is just completely the wrong sort of term. When do you get x cubed y to the 5? Well, you want x cubed, that must have come from, you know, where does that come from? I suppose that must be from, I must have chosen this xy term. You know, everything I get out is going to be something like 1 to the a, xy to the b, y squared to the n minus a minus b or something, or say to the c. It's going to be some product of these things. I suppose I want xy cubed, this is not true yet, xy cubed times y squared. Okay, so I want to pick up xy 3 times, and I want to pick up a y squared once. A couple of different ways of thinking about this. One is to say, well, like I was thinking before, I want to choose brackets. So we're thinking about, where did these x, y's and y squared come from? So as I multiply out these brackets, I can pick up some 1s as I multiply out terms. I can pick up some xy's. Maybe I pick xy here and xy here, and then xy from the last bracket as well. That'll give me my 3 xy's. I need to pick up a y squared somewhere as well. I've got lots of different ways to do that, lots of different combinations. So I suppose I could choose, in general, I could choose 3 brackets to give an xy, then choose 1 from the remainder, one of the other brackets, to give y squared. And thinking about it like that gives me something like, I want n choose 3 multiplied by n minus 3 choose 1. I think I can actually simplify that a little bit. So you can multiply, you expand what those binomial coefficients are and simplify it down a little bit. Or you can think about it in a different way as well. So I'm going to not do algebra on that. I'm going to show you a different way to think about it, inspired by what somebody said for the previous part of the question, actually. So someone on the previous part of the question said, I've got a different way to think about it. I want 4 special brackets. So a different way to think about it is 4 special brackets. So choose your special brackets and choose 4. And then out of my special brackets, I want one to be y squared. Rest are going to be xy terms. So I should multiply n choose 4 by 4 choose 1. And the logic here is I'm picking out 4 brackets out of the n to be not 1s. These are the special brackets, just a few of them that are going to give me x or y, xy or y squared. I don't want very many x's and y's, so just 4 of these. Just show me 4 brackets where it's not 1, and then choose one of those, because in one of those cases I want a y squared, and in the others I'll take the xy. So that's n choose 4 times 4 choose 1. Of course, 4 choose 1 is the number 4, so this is just 4 times n choose 4. here's my approach to the question. Let's just find its stationary points. We're really good at finding stationary points. Let's just differentiate it and find out what happens. So differentiate. dy by dx is equal to 6x squared minus 12x plus 5. I guess I want to know how many roots this has got. How many roots? So I want to know, is the discriminant of this quadratic positive, negative, equal to 0? And I guess I'm just going to work out the discriminant of this quadratic. So the discriminant here is b squared minus 4ac. Trying to be really careful because doing maths on the live stream is not my strong suit. 144 minus 120 is 24. That's bigger than 0. That means that this quadratic has 2 roots. Each root gives me, they're 2 distinct roots because this discriminant is strictly positive. The distinct roots give me different solutions to dy by dx, and each of those is a stationary point. So the answer is C, I hope. So a terrible way of doing this question, which we mentioned briefly, would be to multiply out everything. And I really don't recommend that because of these powers of 4 and 6 and things. There's just so many terms to multiply out that it would just be hugely painful. But probably what you do is if you start trying something like that, is you might realise that if we only want the highest power of x, then along the way we can throw away stuff that's not giving us the highest power of x. I suppose just looking at this smallest version of the problem, where maybe we just looked at this bracket over here. If you wanted to find the highest power of x of just this bit, then you wouldn't bother multiplying it all out cubed. You would say, well, if I want the highest power of x, then I should take the highest power of x from each of these sort of 3 brackets. That's what the cube means. There's 3 of these brackets multiplied together. I should take the highest power of x in each case. And if I do that, then I'll get 2x to the 6 cubed. That would be my highest power of x. And in fact, if we don't care about the coefficient, so here are all of the options, we don't care about the coefficient. I don't even need to worry about this 2. So I would just think about this x to the 6 cubed. I would say, this is going to be a term, this boxed bit is going to give me an x to the 18 over here. Okay, in that box. Okay, cool. That gives me a way into this because now I can go one step bigger and I can keep thinking about what happens when I multiply out these brackets, just ignoring everything that's not the biggest term. I want the highest power of x, and I'm going to make that greedily by making sure I have the highest power of x along the way. So similarly, this thing here is going to be like x to the 32. X to the 32 is a much bigger power because x to the 8 to the 4. That's much more important than this x to the 18 stuff. So that when I come to do this thing to the power of 5, let's forget about the x to the 18. Who cares about the x to the 18? I've got an x to the 32 over here. So I should be doing something like that. So let's put this square bracket, so combining these together. Oh, this is getting a bit messy, isn't it? Combining this together to the 5 up to here. There we go. Maybe I should swap colours at some point. I'm going to just use this x to 32 to the 5. That's going to give me a thing that looks like x to the 160, right? 150, 160. Okay. So that's what this square bracket to the 5 thing looks like. It's like x to the 160. Okay. Over here, what's going on in this square bracket? I'm going to go back down to the smallest level, and I'm going to think about these round brackets. Who cares about this x squared? I've got an x to the 5 over here. So this thing is going to be like x to the 25. 5 to the 5. And this thing over here, who cares about this 6? It's tiny. I've got an x to the 7 over here. So this thing in round brackets, the 4, is going to be like x to the 28. So actually, now I've done that, I don't care about this x to the 25. I've got an x to the 28 to play with. Okay, square bracket term. So that's to the power of 6. That's going to give me x to the 28 to the 6. Forget about this x to the 25. X to the 28, that's exciting. Biggest power of x only. Third time lucky. 168. 120, 48, 168. Yeah. That's bigger than 160. Oh, 168 is bigger than 160. Wow. So when I compare these two big blobs, I've got the curly braces left. I'm going to do this to the power of 3. Who cares about this x to the 160? I've got x to the 168 over here. The power of 3 is one last multiplication. I've got to do 168 times 3. That's going to be 3 times 24, 180. Look, I'm doing it slowly this time. 504, brilliant. I get a D. X to the 504 for my final answer from raising this thing to the power of 3. Phew, I've got one of the options eventually. So when this is divided by x minus 1, the remainder is, and the fact that we're going to use to get started with this question is this fact that when it's divided by x minus 1, so it will be x minus 1 times q of x plus some number, like a, for the remainder. So here, if this is p of x, then we'll write p of x as x minus 1 times q of x plus a. And the trick that we always use for these, when you write it as x minus 1 times some other polynomial plus a remainder, is to think about what p of 1 is. Because p of 1 will kill off this term, 0 times q of 1 plus a, and just leave us with a. So what we really want is this remainder. We want this remainder, which is a, and the thing we're going to work out is p of 1. This is called the factor theorem, I think. This relationship between p of 1 and the remainder. Okay, so we want p of 1. So p of 1 is, brilliantly, x to the 49 is awful to work out unless x is 1 or 0. So this is going to be 1 plus 3 plus 5 plus 7 plus ... plus 99. So we've got to do an arithmetic progression. I can see it's an arithmetic progression because, well, it's the sum of the odd numbers. It starts with 1 and it's got this common difference of 2, which I spotted as I was writing those out. So this is an arithmetic progression. And I know a formula for doing these, which I'm going to get wrong. I can already see coming up ahead of me that I'm going to get this one wrong. There are 50 terms, and the average term is also 50, so I think this is 2,500. Who's with me? What do we want? So we want this polynomial, n squared. Look at this polynomial, by the way. It's got the coefficients have got n's in, the powers have got n's in, except for this 7. This last term's got no n's in it, was a bit weird. We want it to have x squared minus 1 as a factor. So if this has got x squared minus 1 as a factor, then it sort of must be the case that we can write it as x squared minus 1 times q of x. I'm sort of using a similar trick. We must be able to write it as like x squared minus 1 times q of x for some q of x. People in chat have spotted that this is difference of two squares. This is x minus 1 times x plus 1. So this is like saying it's got x minus 1 as a factor and it's got x plus 1 as a factor. So we should think about plugging in 1 and minus 1 and see what happens. So if we plug in 1 and minus 1, then over here, when I plug in 1, I'll get n squared, plugging in 1 is easy, n squared minus 25n plus 150. That's got to be 0. Because when I plug in 1, I get 0 over here. It doesn't matter what q of x is, I'm plugging in 1 so that this thing on the right hand side is 0. So I must have this, and I must have, when I plug in minus 1, I must have, what is this, minus n squared. So minus 1 to the 2n plus 3. This thing is odd, so this is minus 1 to the odd, so that's minus 1. This thing, when n is even, hang on a minute, so this is minus 25n minus 1 to the n plus 1. I don't know about this. Plus 150. Oh wait, no, minus 1 to the 7 is minus 1. So minus 150. I want that to be 0 as well. Okay, ugh, that's a bit horrible. So I've got a quadratic, and then I've got another quadratic that's got kind of -1 in it as well. Let's not think about that yet. Let's think about this one first. So this quadratic's got 2 roots, because this is n minus 15, n minus 10. I promise I factorised that. I didn't just look at the options in the question. I promise you I factorised it. So that's got 2 roots. 10 is 15. So it's 10 or n equals 15. So there are 2 numbers that work in there. But then we should check our answers. We should check whether this works or not. Okay, so I should check in this one as well. I suppose this says if n is even, then this works out as a minus sign. So this second equation will be exactly the same as the first one with a minus sign on each term. So if n is even, we're same equation. So we're going to be okay. 10 is even. So when I plug in 10, I am going to get 0 out of this, because I'm going to get it exactly minus of the thing I had before. Minus 0 is 0. But when I plug in 15, it turns out that this doesn't work. So check n equals 15. N equals 15 doesn't work in the second one. Oh dear. Okay. So when n is 15, this equation is not 0. The second equation. It kind of differs by a factor of 25n, which is not 0. So quick summary: if n is 15, then this has a factor of x minus 1, but not x plus 1. If n equals 10, this has a factor of x minus 1 and x plus 1, which is what we need to have x squared minus 1 as a factor. So 15, not okay, doesn't have x plus 1 as a factor. 10 works out fine, so that's just B. Here's a different way of getting into the question, which I've seen some people talking about in chat, which is to think about this in terms of powers of 2. So some people in the chat have said, I can turn 8 to the x into 2 to the 3x, or even 2 to the x cubed, because that's what this means. This is x lots of 8 multiplied together, which is 8 is 2 to the 3, so that's like 3x lots of 2 multiplied together. So that's this. Plus 4 is equal to 2 to the x squared plus, and then to really drive home the point, I'm going to take, this is 2 to the x times 2 times 2. So this is 4 times 2 to the x. So you can rearrange it like this, and the reason you do it like that is to make it look like this thing where we're going to do a substitution. We're going to do a substitution in something like y is 2 to the x in a moment, but to make it look like a cubic. And the way I think I got to that was by thinking about what this 8 to the x is, and why it's all the numbers in this question are powers of 2, and is that a coincidence or is that something I can exploit? It turns out we can exploit that to write this as something like a cubic like this. So now I'm going to concentrate and write down what this is. Yeah, I want this. I want to know how many solutions this has got. So now I need to think about how many solutions this cubic has got. That's going to come down to, I guess, sketching this cubic or something like that. Or trying to find roots of this cubic. Can I find any roots of this cubic? I wonder. Yeah, so 1 is a root of this cubic. I'm going to spot that 1's a root of this cubic because it's 1 minus 1 minus 4 plus 4. And then factorise that out, and I'll get y squared, so it's y squared minus y squared. And I want, I think, a 4 here. So I want a 4 minus 4. Yeah, I think I want a 4 here. So that's got roots, hang on, I can do difference of 2 squares over here. And it's possible to get too excited at this stage and say these are roots 1, 2, minus 2. But let's not forget, y was supposed to be 2 to the x. So we want positive roots. We want positive roots, so we should probably take y is 1 or 2. And that happens when x is 0 or 1. That's not an option. Like, no. So x is 0 and 1. So actually there's 3 solutions for y, but when you remember that y is 2 to the x, only 2 of those correspond to actual real values of x. I suppose that's why it says real so many times, because we're thinking about real solutions here for x. Okay, so I think I get 2 real solutions out the end for what that is. So similar method. Now we've seen the previous one. We've now, I guess, learned that skill, or it's in the toolbox now, of something we can do when we see new questions. If the bases look suspiciously similar, then it might be an idea to rewrite everything in terms of a common base. I suppose that's sometimes a trick for logarithms as well, isn't it? This common base idea. It's a trick for adding fractions together as well, but let's not think about that now. This 9x, I'm going to write as 3 to the 2x. This is 3 to the x plus 1. Or maybe I'm going to write that as 3 to the x times 3 is equal to k. And now I'm smiling because I've turned this into like some polynomial in 3 to the x. This thing, 9 is related to 3 by being 3 squared, and that helps me relate everything here in terms of 3 to the x. Or said differently, I'm going to try and do a substitution to think about y equals 3 to the x for this one. And then I want to solve y squared minus 3y minus k is equal to 0. I've moved the k over to the side. I want to know when that has one or more real solutions. So I want one or more solutions if discriminant is, let's get this right, bigger than or equal to 0. That will be b squared minus 4ac is bigger than or equal to 0. So I would like k to be bigger than or equal to minus 9 over 4. Quick check. When I do that, quick little worry here. When I do that, I still want y to be positive, like in the previous question. I want y to be a positive thing. Technically, so far, I should probably check that this has positive roots, right? Like the roots to this are 3 plus or minus root of the discriminant 9 plus 4k. Because if it's got one or more roots but they're both negative, then I get solutions for y that don't turn into solutions for x. So just to make sure I get one or more solutions for x, I just need to make sure that I get a positive solution. And luckily 3, this thing with plus, definitely positive. Phew. Okay, right, cool. So this question is quite friendly. I don't get punished for forgetting about this because 3 plus square root blah is definitely a positive thing. So that one will definitely give me a solution for x when I go and take log base 3 over here. And maybe the other one will too. If k is pretty close to minus 9 over 4, then I get a second solution over there. The question doesn't ask me about that. Yeah, okay, extension. When is it one solution? When is it 2? Okay, the answer is A, by the way.